the University of Victoria in British Columbia, Canada. Dillon has 20 years of experience working in academia, government, and industries. Dillon has research in usability of decision support in electronic records, health big data, data analysis, and text mining with machine learning. Without further ado, please welcome Dr. Dillon Chrimes.
Okay, we're good? All right, thanks very much, Brianna. Great intro. I've been here for a couple years, going on the third year with the School of Health Information Science, and I went through the undergrad and grad programs, so I've been familiar with this program and all the interesting things it has to offer and all the research that it does with the faculty and students for 12 years now, so happy to have this opportunity. So today I'm going to talk about data sets a little bit, public data sets, but mostly on the side of decision trees, how to use decision trees with data or construct decision trees with data sets. Along those lines is the expert systems, which has been around for quite some time. Since the 80s, it kind of propped up, especially in the UK, as kind of that AI, artificial intelligence hype around that time. There's many expert systems that are used today. I'm going to cover a few as best I can. And of course, health informatics is a big player in this. It's all about the features, the attributes of health informatics that can be used for decisions. All right, I gotta move my little thing here. So today's agenda, just cover what expert systems are before we go into the trees and the data. Clinical decision support as well as part of this. Of course, that could be a whole lecture in itself. I'm not going to go into too much detail. There's many books on it, many publications, and the importance of using electronic records for clinical decision support is really very important for our school and how we kind of interact with industry, etc. And then the MySIN, some of you might be familiar with this in the 70s. It started up from Stanford. There was a few people involved. I will talk about that in some detail. Used for blood infections pre-operating room as a tool, as an expert system that has decision trees in the background. From there, I'll talk about a little bit about the trees themselves and some rules and some definitions. I've taught this a little bit. I've modified it for this seminar today, but I've taught part of this lecture in my other class, my AI and healthcare class, and also a little bit in the electronic records and decision support, the HINF 310. Learning, and next is the learning by minimizing heterogeneity. It's kind of a complicated sort of way of describing it. We'll get into reason. Basically, it's about splitting the trees and finding that balance in the data to derive decisions from it. And then I have a few examples, mostly public data that I've been working with to follow suit. And then I have some classroom exercises after this seminar. Hopefully I don't have too many slides. We'll see. But sorry, no, I don't. So the motivation really is about these expert systems as a domain in AI. It's, like I said, it started in the 80s. It's still around. I've talked to Canada Health Infoway about their definition of AI and including expert systems on their site, which they don't. Most people nowadays talk about machine learning. Of course, that's the big one. Very cool. Yeah, and so it is a classic example of AI. It's an art and science of creating these trees. You can manually just, without being an expert, just design them right away and see where it goes, or you can use different tools derived directly from the data to create them and test them and train them using machine learning. So it's a classic example of AI. It also leads to business intelligence as well. You'll see some textbooks back in the day that talk about expert systems for business intelligence. It's kind of narrow in the terms of AI. It's weak. It's not a self-driving car. It doesn't have that autonomous adaptivity. So there is, again, this art and science is narrow, but it goes into the deep knowledge of the field potentially, and we'll talk about that. To get that deep knowledge of the field, there is a manual or knowledge engineering, and to elicit or bring forth some of the information from experts, from physicians like from MySyn and clinicians and so on. Health informaticians as well. All right, so there is a modern AI approach, and I'm taking this from Russell Norvig textbook a little bit from 2021. It's the latest edition. It came out in 2003, and then 2010. Again, machine learning is at the top of the list, and nowadays, at this point in time, because it can train the models, it can learn the diagnostic rules once they're established and go from there. There's mechanisms involved in that training of splitting the data and testing part of it, and then integrating those rules with that trained data set as a test or validation. Another thing about machine learning is there's less elicitation, because going externally outside of the expert system or that decision tree in that expert system takes time, it's expensive. People have different ways of describing things, so on. So once those rules are set, machine learning can take off. Also down here is the neural networks, which is also a big one. 2012-ish was ImageNet. Jeffrey Hinton won a prize for that paper, over 1 million images, mined, and these kind of things to find patterns. So nearest neighbor is one of those kind of pattern finding things. It's also in this modern AI approach. Decision trees are not at the top of the list, but they are very common. There's some studies that show that it's more common than anything else right now still, because of its use in the expert systems, and the fact that it can be readily available to anyone that's interested, kind of thing, or they want to create their own. However, there are rules, I should say, to learning rules. And then I'm going to go into this MySyn as a good example, which once it's set up, there's some automation established. Talking about expert systems and trees without diagrams is a bit abstract. Obviously, we know what knowledge is, documents, for example, we all know what that is. But the way the rules are constructed is a little bit different. It could be paraphrases from the actual summary of what's in the document or text, or from a table, the data, the numbers. In that knowledge representation, those rules exist, and there's conditions or antecedents, and then there's consequences or consequent. These are described in a number of different ways in different textbooks and articles. But for me, I thought that was the best way. If then rules, there's the condition, and then there needs to be a conclusion involved. Otherwise, you don't have a decision tree. And within those conditions and between that conclusion is the axioms, features, or attributes, which really is the health informatics involved in that perspective. There's reasoning processes. This can go into some detail. I kind of summarize it as forward chaining and backward chaining. My interpretation of creating decision trees is both. Again, I feel it's art and science. Obviously, we want to go more to the science side, but it's going to be used in productivity, used in a clinical setting, of course. But there's the going down the tree, which decision trees are kind of an upside down tree. The root is at the top, and then the leaves are on the bottom. So starting at the root, going forward, and then going from the leaves back up is backward chaining. And there's some ways of describing it. A lot of the textbooks refer to forward chaining as data driven, and I'll show some results on that. And more of a progressive space search, going through different search spaces, heuristics included in that. Backward chaining is more on the regression side. You kind of know the outcome already, and you want to create that line, for example, of linear regression. But in this case, you're going through a sequence of data. And the sequence of data is important in these systems because it's not just one linearity going on. There's a couple steps before there's a conclusion. It depends on the data, how much depth there is, and that's where this chaining thing comes in, because there's a sequence of yes, no, towards that decision, for example. MySyn, I'm not an expert in MySyn. To be honest, I've never used it. I haven't seen a prototype. There might be a few things online. There is a few different discrepancies of how many rules they have. I saw one 350, which is here, in this paper from 78, I believe, yeah, by William Van Mel, was part of this development process. I mean, obviously, Shortlift, I'll show them Shortlift and Bruce Buchanan and Randall, those are the main players from Stanford and UCLA, I believe. Again, this rule-based, it's this typical sort of expert system that we would expect. It's medical, it has decisions support, clinical decision support for diagnosing blood infections with probabilities. The rules did acquire extensive expert interviews, and they brought those interviews to the table and into the program and via in the back end of the decision tree. It does capture some elements of uncertainty by introducing probabilities. And so here's a probability here as a conclusion, or going through these three steps in that command line sort of rule-based expert system for MySyn. Gram stain of the organism is gram negative. Morphology of the organism is rod, for example, anaerobic. So 0.6% probability that this is a bacterial. Obviously, if you're a patient or a clinician looking at this and seeing that this patient might have an infection, the surgery would not take place. So it has its place in productivity. And here's a couple. I'll show these papers just coming up. There's Davis and King, and then this very famous kind of paper from Davis, Randolph Davis, Buchanan, Bruce Buchanan, and Edward Shortlift, 1977. Have a look at this paper if you have a chance. It has some interesting, it's historical. It has an interesting way of showing what an expert system looks like, not just about decision trees, but other sort of ways of diagramming it. So you have infectious disease expert on the bottom, then you have physician up top. You have this consultation part of the program, explanation part, which could be here, and then you have the knowledge acquisition, maybe of an input, and then it goes between the patient and sort of this factual knowledge. Here's the famous paper right here, but this one is interesting. 75, it came out. It doesn't talk about MySyn. Well, it's about MySyn. It doesn't go into too much detail about this clinical support. It goes into sort of how it was constructed, and there was three things. There was the rules itself. Rules itself. It's good to know who use MySyn. Oh, Abdul says it's good to know who used MySyn. I believe MySyn was a very academic exercise in AI. I heard, from what I read, Abdul and everyone, that it was used in productivity. But I could do some more literature reviews of that just to make sure, because this is going back in a few decades, right? So, but anyway, rules, database, and interpreter. They have three parts to it. And what I really want to highlight, I mean, the rules, it sort of goes, S equals A, B, A, or whatever that sequence is, and it shows you these sequence, this tree based on that database. They were in this paper, they consider this production system for MySyn as the tree as part of the database. And then they sort of, drew it out. They, XY here, WZ, WY, XZ, and then they have a sequence of these, from the root of the tree to the leaves, the ABC here equals this sort of output. And then maybe they linked XY to a certain, text. For three steps in those, maybe this, this is text as well, going 1, 2, 3, and then they have that conclusion, which has that probability as I showed earlier. So that was interesting. Gives you kind of a pointer for that. System was developed. Oh yeah, nice. Thanks, Alex. Yeah, Alex Kill. System was developed in Stanford School in 1970. Sweet. I think Bruce Buchanan was Edward Shortlift's supervisor, and Dr. Shortlift, who's professor at Columbia now, I believe, or emeritus. He was doing his PhD and MD at the same time. when I read, so I'm just trying to get by myself. So. Anyways, this is a very famous paper, awesome read. The other ones are a little bit abstract, just shows you the actual tree here, patient, infection 1, infection 2, culture 1, culture 2, culture 3. There might have been some cultures that were done during, they started up the tool, sent the culture to the lab, got the lab result, clicked through the tool again, and then they got to some conclusion. So you see there's 4 organisms potentially, and they do identify different organisms in their rules. This is an interesting diagram because it kind of links the knowledge base, which is important, the data and the patient data as well. So the knowledge base linking to the patient data with these 4 programs. A bit more complicated than a decision tree, and then examples I'll show later on, but I thought it's important to show the end result of something that's very historical. Consultation program, explanation program, question answering programs, or part of the program, knowledge acquisition. So bringing in that knowledge from patient to knowledge base and out to the programs. Oh, I see. That's what it was used. But anyways, see here. So this is my kind of tree, not the best tree. I'm not going to go into detail. If you have any questions, it's not used in production at all. I was trying to figure out if I was to do a chatbot with COVID with decision tree, how would it look like based on some literature? And I did, some stratification of, lung from the lungs to the heart, and some serious issues or mild issues, and these kind of things. By no means it's used at all. I teamed up with a company from UK called Busy Rural, and they posted this on their website. They have other medical demos that uses trees. There's one on wound imaging and stuff like this, which is interesting. But one of the things that I found out was I had 212 nodes from just constructing the tree from literature, which is quite big. And then I realized the volume of that 212 equals like 60,000 scenarios. So it just kind of multiplies, it's too big a tree really. It needs to be modified a bit to be used in productivity, from my understanding. And then from those 2012 nodes, I created a table. And the table, I'll go into some tables, but those decision points, those 212 decision points, they're actually columns in the table. And then from those scenarios, there's 900 rows. So it's not a small table. It's, but whether or not it can be used, if that's a question. I did have there's about 1,000 or 900 people that the company had clicking on through this web app and chatbot and stuff. And there is, out of those 900, there is more instances of clicking on not having severe COVID than anything else. So it's kind of an interesting scenario. And usually they went down at least 6. There's up to 9 depth, and 6 was where they kind of landed most of the time. So there's some analytics around trees, decision trees, which I'll talk about. So there's, for mycin, only diagnosis blood infections, kind of narrow, requires extensive expert interviews, so expensive to develop over time. The domains change. If a domain changes, like for blood infections and these kind of things, it cannot be used, obviously. It's brittle, fragile, especially for new cases, these kind of things. Check. ES also have many other challenges. Rules conflict. Yeah, rules conflict. Well, we'll talk about that in a bit. All right. So from the tree to the rules. And again, these are upside down trees, and moving through them in that sequence does give you some information. It does and it also gives you an idea of how the tool would work in the back end. How would the tree link to something that you click on and move through some questioning? It also moves from a table to something more dynamic. The table does potentially cover, the table or Excel sheet or whatever you call it, does cover the actual relevant material and those features. but it doesn't give you an idea of how people would answer the questions, right? So it has that dynamic nature to it, which is, I think, is awesome. And there's decisions. So during the process of decision making, there are multiple features, and it becomes essential to concern the relevance of consequences of each feature, thus assigning the appropriate feature at the root node and traversing the splitting of the nodes downward. So if you don't start off right, you're going to be in the weeds. You're going to be your tree is not actually set up correctly, and you'll notice that right away when you're clicking around. And there's different ways of splitting. We'll talk about that, like the Gini index. Yeah, moving towards the down direction, like the forward chaining a little bit here, leads to decreases in the level of impurity. So the data points get mixed, and I'll talk about that with entropy, how to sort of think about that. And this is very academic, I think, that term, but it does show that the decision points, some of the leaves don't exactly, they end potentially, but they might not be a pure end to that leaf. There might be more to splitting, but they might not be known at that time. Obviously, uncertainty is there with probability, etc. To resolve these from the tree to rules, there's splitting measures like entropy, information gain, and Gini index. Some of these are easy to sort of calculate. Some are a little bit of difficulty. Some applications do actually calculate them for you with loading the data to create the tree, and they bring forth the Gini index or ratio, etc. And I'll show some examples of that. Okay, so decision tree, just let me define it a little bit here. So an explanation of a function that maps a vector of attribute values to a single output value decision. So it maps, so let's say you're driving a car and you want to go to a certain destination. This is brand new city, Victoria, and you're downtown. How do I get out of downtown? So it's, the Google map could actually have a tree in the background or whatever. We know what Google Maps uses tables, but it has those destination points, and then it creates that perfect sort of path, the shortest distance for you on the app. So that's a good example of this. Decision tree reaches its decision by performing a sequence of tests, starting at the root and following the appropriate branch until a leaf is reached. There's Boolean. Mostly there's positive, negative, binary. Absolutely, I'm not going to go past that, but there are decision trees that have more than two. Alrighty, so here's just Boolean output to path. As I mentioned, around my little, maybe I can just minimize this. Oh, there we go. All right, I'm disappeared now. Okay, so again, essentially they're flowcharts. Decision trees are flowcharts. They have these natural order of the sequence, this micro decisions to reach a conclusion. There's a start. They start cascading these Boolean decisions. Either you grab it from the data, you go forward chaining or backward chaining, or you just map it out and then you just kind of maybe test it with data later on and run it with machine learning, et cetera. So it has that cascade effect. And the start point is very important before you start cascading. A set of decision nodes and representing all leaves of the decision tree. So if you don't have decision points on your leaves of your decision tree, you're not quite done yet. So, okay, so I just want to mention one thing that I saw, this Bayes theorem. It's been around for a little while. It does do population, COVID outbreaks, the test results of COVID, how many people are actually that are positive versus negative. There are some just papers that use Bayes with decision trees, but this tree that's made here, that's developed, that I developed, probability is already provided. It's not a decision tree. It's just providing ways of multiplying these numbers to create an answer here, and then to get the answer overall. Out of 10,000 people, number of positive test results of no heart failure equals 392. However, there's Bayes averaging in decision trees. There's other things that I'm not covering, and obviously Bayes is very important in this public health sort of population health analysis. This is more like a decision tree. For example, you have patients with history of allergies. You go yes or no. No vaccine can be given. Any concerns, etc. I'm sure you've seen some of these flow charts. online or at the vaccine clinics, etc., for Island Health here or elsewhere. Or yes, then same vaccine, other allergic reactions, and they would have, experts creating this, or maybe it's from the World Health Organization, who knows? And then they have minutes here, and then so forth. And then each leaf here you'll see has a decision point. It doesn't branch out again. So this is the decision tree. Another thing is using decision trees. This organization in the US, the Agency for Healthcare Research and Quality, they do define decision trees, and they do talk about analytic frameworks. And part of that framework could be a decision tree, and they give some suggestions. Decision trees can be used in conjunction with analytic frameworks to illustrate the potential impact of test results on management decisions and outcomes, provide further clinical context to the topic, clarify key questions by identifying relevant indices in the diagnostic accuracy, blah, 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 revealing which range of possible pathways, again, and outcomes logically flowing from a test result. Canada Health Info doesn't have a definition for decision trees. And like I mentioned, expert systems seems to be a little bit lacking there. I've asked them a few times, but I mean, they've got lots of information. I'm not going to downplay them at all, but and so on. But so this another thing with this AHRQ, they give some examples on their website. This one's from 2002. It's on full field digital mammography, so screening for breast cancer. And they kind of go into performing full field, performing screen film, and they go towards biopsy, positive, negative, and then from that positive biopsy initiate treatment, for example. So there are decisions on these points here, and this is the leaf. This is the tree on the not top down, but left to right, facing it. So there's a number of examples like that. I want to show the diagram first before I start talking about different parts of the diagram, because it's a little bit abstract. Pictures 1,000 words. Knowledge engineering problems for flowcharts. One of the things that I found and I kind of talk about this in class, and I think that's one thing that text analytics brings forth is that some of the language used as knowledge, it's a little bit difficult to interpret. For example, this one, any one of the following. So how would you use that in a tree? That's a good question. Two or more of the following. Maybe that's part of the tree. Incompleteness. So like for example, in the is difficult. There's different logic levels of logic in the writing. If you're developing a tree from the writing or interviews, etc. There's some inconsistencies as well when you're trying to reach one decision or a set of decisions, whether to do a bone scan or something or a CT, MRI. There's, obviously there's clinical decisions in the background, but sometimes there's it's not, there's a gray area. Okay, all right. So for the class that I try, and there's one reason why I'm introducing this Orcan's razor, which is basically don't continue multiplying everything together. It's too complex. Try to keep it simple. Simplest explanation that covers the data is best. And then from there, you'll see stuff like greedy boosted gradient and greedy decision tree in the literature, which just sounds really weird to me when I first read it. I'm like, what the hell does that mean? But that's where it's coming from. It's coming from this keep it simple. The smallest tree consistent with the samples will be best predictor for the new data. Finding all trees and finding smallest, it can be expensive. Like my COVID example that I tried that tree, I have too many nodes. I really need to go down before I can actually test it with data. Testing with data would take quite some time. Finding all of those 212 parameters. So greedily build a small tree. That's what the literature is saying. Decision tables there's decision tables, there's decision lists, and there's decision trees. Again, the tables, as part of a flow chart, it's the spreadsheet, from those nodes and decision points, they should be columns, and then those rows are those actual decisions, whether or not they in that column it landed, et cetera, at a specific decision. You don't know that until you actually put it in a tree. But it gives you an idea of the matrix involved in these tables. And usually the literature starts off with the tables and then goes to the trees, from what I've seen, or random forests, which I'll talk about. We pack more into a smaller space if we relinquish some control on indicating the order of micro decisions. A decision table has one row per rule, one column per decision variable, an additional column for the decision to take when that rule evaluates to be true. This is from '97, Handbook of Medical Informatics, kind of a famous book. And there's lots of different ways to show these decision tables. This is one of them. Again, these rules, the columns that result from those rules, and then the sort of diagnostic expressions here. So seeing the table, you understand what I was trying to say in terms of the 212, you know, 900, etc. This is a kind of a textbook example, again, sunburn example. You have people, their hair color, their height, weight, and then whether or not they use lotion or not. We're a little bit past summer now, but we did have a pretty nice October. So before I go into that, the goal is to kind of label these examples, predict sunburn or not, and then have this match of these features and output. You could use nearest neighbor style. I'm not going to go into too much detail on that right now. The better solution is to identify the tree, start at the top, and then move down, divide into subsets if you need to, and then assign value at the leaves and see where that goes. So for example, you could use hair color, whether or not this is true or not. Well, it does kind of mimic what is in the table, right? So you have hair color, blonde and brown, red, and Emily's the only one with red, and she got a sunburn, fortunately. And then there's lotion used, and some, you know, did or didn't. So the ones that did use lotion didn't. So there's a decision point here, etc. Not to go into too much detail, there's lists. They consist of a series of tests. Lists can be used. This is from that Norvig, Russell Norvig. Russell is at UCLA Berkeley, and I believe Norvig studied his PhD there with Russell. Again, that was that 2021 textbook that came out first in 2003. And they do give some pseudocodes, what's interesting, and they do compare trees to lists. So lists can be part of this solution to just creating decision points. But there's usually the studies are showing that there is a benefit. There's a little bit higher proportion correct on test results or test set using trees than a list. And of course, there's computation, right? You have a list, it's much more computational heavy than a tree. Okay, splitting measures. This is the important part. This is really defines a tree. If you don't have splitting measures, you don't have a tree. One attribute taking part in decision-making process is necessary to decide the relevance and importance of each of the attributes, thus placing the most relevant at the root node and further traversing down by splitting the nodes. And again, there's applications that find that top root node, or there's other ways to do it, to calculate it. Part of this splitting is the information gain. It's used to determine which features and attributes give us the maximum value. And here's a good example here of a good entropy, of good information gain. You split, you have the data set here, plus and negatives or whatever, and then you split it perfectly. You got negatives and negatives in their decision at that point. Have the same data set here, whatever that splitting measure it is or was, you split the data, but it's not perfect. You might have another split here, for example. So information gain can be used. Part of this is the concept of entropy, provides some degree of uncertainty, and there's a calculation involved. There's a formula. Aims to reduce the level of entropy starting from the root node to leaf nodes. Leaf nodes, I should say leaf there, but apologies. When speaking about historical AI, says it would be good for students to look at the paper FT Dombal on computer-aided diagnosis acute abnormal pain. It uses Bayes' rule. Okay, cool. Thanks, Abdul. So This formula here, this uses a log. It's not as the information gain is used much more than this entropy nowadays, and there's also boosted gradient and stuff, random forest. These groupings of these trees, but I'll talk about that if I have enough time. It's information theory metric that measures the impurity of uncertainty in a group of observations. This shows, negative, positives, mixed, and then you're up here. You want to hit around 1. If you're at 0, I'll show that it's not a good entropy. It's not a good data set to use or tree to use. It's not, again, entropy is not preferred over the log function as it increases the computational complexity. And you kind of want to minimize the loss per se, but you're not actually calculating here. The information gain, you're kind of going on the other side of the fence. And this is a good example of entropy. You have class A and B, there cannot be split, so entropy is 0. If you have class A and B as 5 and 5, you can split them in half, so entropy is 1. So our sunburn example, oh, got another shot here. Okay. All right, camera. Little chatting going on. All right, so I know it's not the best thing to show formulas, but it just gives you an idea. Some applications can do this for you nowadays, but I try not to show too many formulas because there's always questions about them, and that's a good thing. But I just want to show them and then go after the seminar and talk to class. Any questions like that, I can review them. Sunburn example again from there's height, weight here. Didn't use hair color and lotion. It shows that weight actually from the calculation is actually 1 entropy, so that should be used in that tree. More maybe the main splitter in the beginning compared to height and lotion, which could go afterwards because it has that 1 that we're looking for. Here's another example. This is an impurity kind of more academic sort of way of describing it. These circles, and then there's pluses here and circles. There's maximum impurity here. So you have that linkage, you have that log of these data for a good training set, whereas this one, you cannot split it, obviously. So it's minimum purity, so it equals 0. Here's another calculation. So you have the entire population here, 30 instances or whatever, these circles and pluses, and you can split them, 17 instances here, 13, however that was done. And then there's calculations for each of these child entropies with the parent, and then you get towards the actual information gain in that calculation. So the parent minus the child's and the child weighted average entropy of the children, and then it equals 0.38, which is not too bad. You want to be around 0.2 usually, and that's usually the Gini index has that value between 0.2 and 0.3. Gini index. The hierarchical structure of a decision tree leads to a final outcome traversing through the nodes of the tree. Each node consists of an attribute. Which attribute should be placed at the root node? Again, that's something we need to figure out. Which feature will act as internal nodes or leaves? We need to figure that out. And then to decide, we have our splitting measures. The gain ratio takes into account a number of branches splitting. It is less resource intensive compared to information gain. And boosted grading is part of this groupings that was on Kaggle that goes further from the Gini index. Here's the formula. Gini index, unlike the information gain, isn't computational intensive as it does involve the log function used to calculate entropy. This is why Gini index is preferred over information gain. It's a number of ways of calculating it. We have, A and B, A over A plus B in this curve. It's called the Lorentz curve. It was founded by a statistician from Italy named Corrado Gini in 1912. I do have some calculations here, but I'm probably going to have to chat with the class about this. But there's, this is the stock market and low and high interest, trading volumes, and then the return. And you can calculate the Gini index from this example. based on those attributes, and then 0.27, which is not too bad. And the Gini index versus information gain, there's some discussion about it, creating decisions. You might want to start off with the information gain. I've seen trees that kind of mix between them. There is this ID3, which Abdul, Alex know about, that came out in 1986 by Ross Quinlan. It's a program that uses decision trees. And then this later on in the 90s, I think it was 93 or 4, something like that. This same fellow, Ross Quinlan, has a C4-5. Regression trees are part of this. Obviously, they use more stats. So another example I have just quickly is a restaurant example. Patrons, wait times. Are they hungry? Then they go this way. If there's an alternative, then maybe they can rent a reservation instead. So, but also what I wanted to highlight here is there is heuristics involved. You can, when you're creating these trees, you're splitting measures, but maybe you want to start off by categorizing things in these trees for each of those nodes, and then go towards more figuring out whether or not they're splitting correctly. Here, obviously, this is this is a bad example of a tree, and this is a better example of a tree. There's some recursive problems. So if the remaining examples are all positive, then we're done. Great, we have decisions on each leaf. We can use that tree to test or use it in a productive way. If there are some positive and some negative examples, then choose the best alternative to split them. For example, the hungry being split from the remaining of the restaurant example above. So you see hungry here. There is some splitting potential at yes. If there are no examples left, it means no example has been observed for this combination of attribute values. We return most common output value from the set of values that were used in construction of parent nodes. So there might be a somewhat complete tree, but maybe not quite as we wanted. If there are no attributes left, but both positive and negative example, it means that these trees have exactly the same description, but different classifications. Maybe there's some issues with the data quality. We might not be able to have that tree quite yet. We can evaluate the performance of these trees in a number of different ways. I showed this earlier with training size versus the correct test. There's pruning, which I don't have time to go into. The trees, you can figure out which paths are more common or which paths are easily detected with the input data, so they can go through the tree quicker. So that's pruning. Unfortunately, trees do, especially the ones that you create yourself in the more artistic way, there's overfitting. My tree on my example for COVID, it's big, it's overfitting the data large. I don't even know actually if that tree could include part of the data or all of the data at this point in time, but there is definitely some overfitting involved, which means it's trying to get to that decision without having all that data, or at least having as part of that data and making that decision before it should have been split that way. So overfitting. Machine learning also has this overfitting attribute sometimes with training the data to perfection, and then unfortunately testing it outside of its data set and not being valid. So part of that overfitting. Community trees are single decision maker. How to deal with a group decision problem, consultation. Okay, I'll get into that, Alex. I have some examples coming up. So ensemble learning and groupings is a newer concept in the late 90s, showed up till now. It's used in competitions, for example, this boosted gradient or gradient boosting and random forest. Random forest is trying to handle the overfitting, trying to grab that data. Maybe there's more than one tree to decide on, and then from a group of trees, it creates that best possible tree. Boosted gradient has very complicated math, more stats related. It does try to, it can overfit for sure. It does try to deal with it. There's a sequential classifiers that you can benefit from using it. Here's a random forest. So you start off in a certain way. There's oranges, bananas, etc. You have apples, and bananas. And then from those two trees, the majority of those, or three trees, the majority is the apples. So that's basically how that works. I don't want to go into too much detail. There's obviously random forest is an AI tool. It can deal with regression. It operates by constructing a multitude of decision trees at training time and outputting the class that is the mode of the classes, etc. There's a lot of different ways of describing it, but the best way is it is a multiple of trees and it derives the best possible tree. There's also stacking and boosting. You stack the trees, you get a certain amount. This is going a little bit advanced into more regression, sort of stats based. And then the boosting itself goes into that as well. Boosting example, this add-up boost, it was in 1996 introduced, so quite a while ago. It's very famous, and it tweaks the weights in that boosted gradient in those calculations, and then it does these 2 iterations here, and it creates that train classifier at that point in time. So there's plus minuses here, and then you'll see it covers the data much better than the second iteration for the first. Talk about this. Again, there's mean square errors as part of this loss function for boosted gradient, developed in the late 90s, and it looks more at the loss than the information gain. It's a popular AI kind of tool to use at this point right now. There's a lot of different studies on it, from training the data set towards the best possible index or loss index or ratio. There's multiple boosted gradients that can be run simultaneously. YouTube here. Okay, I have a few examples. Okay, so this example here, this data is from UCI, Machine Learning Repository. It's drag and drop kind of interface, and you combine certain parts, you load the data, partition it, and then you create a tree. In that application, this is from heart failure. It creates these decision trees. There's two selection points. There's Gini index and Gini, the ratio. So it gives you an idea. Here's the actual where it's located. Here's the data set itself. There's a paper published in 2020 based on this data set. Here's the data again. So there's 13 columns, and there's zeros and ones for death event. I use the tool to check the data, and then notice there's this value that shows up more, and basically the data is a bit manipulated, so they put an average in the data. Machine Learning Studio I used for this data set as well, getting some kind of scoring, making sure that data can be used for some sort of prediction. Again, going back to the tree. This KNIME gives you a good detail of all the different aspects of creating a decision tree from the data. And again, you could reconfigure it, run it. And so there's 2 trees I created. One is this one here was time, and then age, less than or equal to 69 or greater than 69. And then there's this serum creatine, less than or equal to 1.55, greater than 1.55. And then also time showed up again. So and then this one here is time, same as age, different level of creatine, and then there is ejection fraction, less than or equal to 32.5 or greater than 32.5. I'm not a clinician, so I'm just showing you some examples here. Same data set you can use through RapidMiner. KNIME has developed the latest edition, came out in 2022 March. So it's an awesome tool. It's open source, free. Check it out. There's also a paid version. RapidMiner, there's an educational version that's free. It's very similar. They actually have more. They have 5 different ways of splitting here, and you can. It's drag and drop, and you can load data on this interface, run a tree or boost a gradient or a random forest, and get an output. Another one is Orange. It's from Lithuania. I think, yeah, KNIME is from Switzerland initially, and this is from Germany, and this is from Lithuania. Open source, free. You can install it on using Windows. It can create similar random forest trees, very similar style. It actually links the file, links to that UCI repository. It has actually linkages to that. You don't even need to load it, but you can actually load data as well. Orange, yeah. Orange 3, I believe. Yeah,
Orange needs to be integrated with Anaconda.
I use Anaconda because I don't know, I'm trying to check it out, but you don't need to use orange with Anaconda. Weka is another product. It's been around since the late 90s, uses machine learning, won some awards in mid 2005-ish or something like that. Same data set, age and creatine. I'm not a clinician. I don't want to, go into too much detail because I'm in the weeds then, so I'm in trouble. Anyways, I shouldn't say that, but anyways, yeah. Just to show you that you can use the same data set in a different tool and run it through different sort of gradient boosting, different greedy stepwise here. It shows you age, ejection fraction, serum sodium, and time as the 5 attributes that were selected.
Cardiovascular risk.
Yeah, it's been there's papers that use this that I've seen recently that use this tool. Open source from New Zealand. This paper I thought was interesting. It gives you some tables in it. It gives you some categorical values. It gives you also how they found the feature importance. So the AST, lymph nodes, LDH, etc. It's on infections, COVID-19 infections from routine blood exams with machine learning. And then from the tree, you see the ACT lymph nodes. And it goes from that order in this tree on this left to right towards the, maybe not a decision, but it gives you the accuracy of that could be used in the decision. This one is an interesting paper, came out 2013. Medical diagnoses, automated medical diagnoses, has a flow chart and then a tree behind it, has different character attributes here. More bioinformatics, like cell types and stuff like this. And then here's the tree it's created here. You'll see some of the attributes have percentages linked to it, different values. Sometimes these trees in the research they post the actual Gini coefficient in the block here to give you an idea of what the degree of splitting was in that measure. All right. In summary, decision trees are a basic design knowledge representation technique for logical, rule-based, Boolean, predicate-driven decisions. Decision tables let you compactly compile a host of decisions on a fixed set of decision variables. These take you very close to the representation needed to encode production rules for an interface engine. I mean, that's really the ultimate goal of creating these trees, especially in health informatics, is to see whether or not this could be used more than once, right? Rule induction from data provides an alternative to conventional knowledge engineering. Computer figures out rules that fit past decisions instead of you pursuing experts to ask them what rules they use. It creates this sort of interface. I mean, it could also benefit the clinical decision support, providers could use it, etc. Another thing I didn't have a list here is that there's a lot of public, especially COVID, there's a lot of public data online. And it's interesting sometimes just plugging it in and see if a tree can be created out of it, because you don't know right away whether or not they could be used. I mean, obviously, if the COVID data is on location and positive and negative, there's no tree. But if it has COVID with symptoms, positive and negative, there could be a tree. Yep. Alrighty, thanks very much. I'll stop. I'll just keep sharing.
Yeah, that was awesome. Thank you so much for that.
I do have some examples. Kind of breeze through parts of it.